All right, so on the previous board, we've seen that we can write n sigma hat squared over sigma squared as the norm of I equals to 2 up to n vi transpose y squared, where y is a vector composed of x1 minus mu over sigma up to xn minus mu over sigma. So in effect, it follows a multivariate normal distribution that's centered and has covariance matrix the identity in n dimensions. And V was defined as V1 up to Vn, an orthogonal matrix. And V1 was a rescaled version of the all ones vector. But now that we have arrived here, I think we can forget about where it came from and just say that this is an orthogonal matrix. And let's now actually, let me rewrite this in terms of V2, and let's call the submatrix here W. So basically, the matrix that I get from dropping the first column from V, I call W. And this is now going to live in R. Let's see, it's still going to be an n, still going to have n rows and n minus 1 columns. So it's going to be an n times n minus 1 matrix. Why do I do this? Because now this can actually be written as reversing the steps we did on the previous board. This is W transpose. And W is still composed of orthogonal columns. So this is norm squared of W transpose Y. Now remember the calculation we did on the previous, or 2 boards back actually, telling you that this means I have a certain subspace. I project y into that subspace. I get some coordinates in the W matrix, and I bring it back into the original space. So that means that this W application does not change the norm, and I get the norm of W transpose Y. Now, what is this? This is a vector that lives in Rn minus 1. Remember, W is an n by n minus 1 matrix, so W transpose is n minus 1 times n. This is a linear transformation of a normal vector. So this is also going to be a multivariate normal vector. And I take the squared Euclidean norm of that vector. Now let's try to understand the distribution of this vector here. We know the mean is going to be 0 because it's a linear map applied to 0. And its covariance matrix, let's just write it as covariance of W transpose Y, I get by multiplying W transpose times the covariance matrix of Y times W transpose transpose, which is just W. Plugging in the identity gives me this. And again, because W is composed of orthogonal vectors, this is the identity matrix in n minus 1 dimensions. So in fact, this quantity is the Euclidean squared norm of a Gaussian vector, of a Gaussian independent vector, standard normal in n minus 1 dimensions. In other words, by the definition you've seen in class, if I divide this quantity, so this quantity was n times sigma hat squared divided by sigma squared. If I divide this quantity by n minus 1, then this follows a chi-squared distribution with n minus 1 degrees of freedom. Perfect. So now, after a lot of work, we actually understand the distribution of this exactly. So this is not an asymptotic statement. We've just shown that it exactly follows a chi-squared distribution. One more caveat, though. Remember back to what we want to do with our test statistic. We want to normalize by this distribution. That means we actually take another random quantity, namely something that depends on mu hat, and we divide it by this chi-squared distribution, you can already see where this is going. What we want to have is a t distribution at the end of the day. One more thing is missing. We have to show that this chi-squared distribution is actually independent of the normal distribution I want to have in the numerator of this quantity. So remember what I was just saying is we were considering this quantity which is not quite our test statistic yet, which is going to look like mu minus mu hat square root n over sigma squared. And we know that this here is n01, but we want to replace sigma squared by sigma hat squared. How do we do this? We already have everything in place to show it. Namely, we know that mu hat is actually, remember, mu hat is mu hat is, I have a normalization going on, 1 over square root n times V1 transpose x. And that means I can also write it in terms of y, if I can get the normalization right. So this is going to be mu plus sigma times 1 over square root n v1 transpose times y. So if I plug in y, let's see what happens. I take all the x's, I subtract off mu, I divide by sigma, so that cancels out this sigma. And the mu, if I sum it up n times, I just get the mu back. Perfect. So actually, all we have to understand is how does wt times y depend, or how is the connection between w transpose y and v1 transpose y? This we know because w comes from an orthogonal matrix. So let's first calculate the covariance between w transpose y and v1 transpose y. So, and this is actually, so this is basically part of the big covariance matrix given by v transpose y. So this is an n-1 vector, and this is actually just a number. So since both are mean 0, this is the expectation of w transpose y. So this is going to be a vector at the end of the day. And let's flip this. Because it's just a number, I can flip the order here. Y transpose v1, which is, these are linear and fixed, so I can write it as w transpose expectation y transpose v1. This is the identity matrix in n dimensions. So it's w transpose times v1. And this is exactly the collection of the inner products of all vectors v2 up to vn with v1, which by definition is the all zeros vector in our n-1. So actually, these two random variables are uncorrelated. And since they are jointly Gaussian, they are independent. So that means w transpose y is independent from v1 transpose y. And now the rest of these statements only involve fixed quantities, no random quantities anymore. And that means, in effect, sigma hat squared is independent of mu hat, or these two quantities are independent. So that means that I can actually write down the test statistic I want to use. That finally means that, so first let's think about a pivot. The pivot is going to be tn tilde 2. That's why I put a 1 there. Oh, I made the mistake of writing 2 here. This was 1. Sorry. T tilde 2 is mu minus mu hat times square root n, okay, over sigma squared Now this is normal, we know that, but I need to get rid of the sigma squared. So I divide this whole quantity by the quantity that we've just shown to be the square root of this quantity here, by square root n over n minus 1, square root sigma hat squared, and I forgot the square root again here, and also there, sigma hat squared over sigma squared. Now n cancels out. Sigma squared cancels out. This is why we did it. And we end up with mu minus mu hat times square root n minus 1 over square root sigma hat squared. And by this consideration, we know that this follows a t distribution with n minus 1 degrees of freedom. And now, finally, to get the pivot we want, namely the actual Tn, we will plug in mu equals 0 for the hypothesis test there. So we end up with minus square root n minus 1 times mu hat over square root sigma hat squared. So there was a lot to digest. Let's briefly recap. So all we wanted to do is actually get a non-asymptotic hypothesis test. And it was pretty clear that if I start from a quantity like this, I can get something that works asymptotically. But the problem was we didn't know how to get rid of the sigma squared here while still understanding the distribution. So what we had to do is take an estimator, sigma hat squared, but then exactly understand its distribution, or in other words, exactly understand the distribution of what happens when I take mu hat and divide by this estimator, sigma hat squared. And that's what we did here. So we showed that we can actually rewrite sigma hat squared as some linear transformation, the norm of some linear transformation of some other random variables. And this allowed us, by linear algebra essentially, to exploit the fact that for Gaussian random variables, we know that uncorrelatedness implies independence. So we understood that the sample variance is actually independent of the sample mean. And we also understood exactly how big the sample variance should be. Namely, it will follow a chi-square distribution. And then afterwards, we just use the definition of a student t distribution as being defined as a standard normal over a chi-squared with over square root of a chi-squared with n minus 1 degrees of freedom. Now, we basically understand 2. And in the next board, we'll try to understand how to adjust S.